So we've now looked at two factors which can help us work out whether a reaction is going to be feasible or not. At the start we looked at enthalpy and the idea it's always going to be favourable for a reaction to be exothermic, it's always going to be unfavourable if it's endothermic. However, we've since looked at the fact we've got another factor to worry about, entropy, which can also affect the feasibility of a reaction. You can calculate the entropy change for a reaction, and if entropy increases across the course of a reaction, that's going to be favourable. If it decreases, it's going to be not favourable. There's actually one final further factor we need to worry about, and it's temperature. The temperature can also affect whether a reaction is going to be feasible or not feasible. In other words, some reactions might work at high temperatures but not low temperatures, and the other way around. It's easier to look at that in an example. So if you think about ice melting into water, so that's just a physical change. So solid H2O is going into liquid H2O. You can analyse in terms of enthalpy and entropy. Melting ice is actually an endothermic process. You might not think about it in that way so much, but if you think about the fact that it takes heat in from the surroundings to melt something, that actually is describing something being endothermic. And what we know about endothermic processes is that they're generally unfavourable. However, if we look at the entropy, when you're splitting a solid up into liquid, we've looked at the fact that that's always going to increase entropy, and increasing entropy is always favourable. So we've kind of got a bit of a contradiction in this reaction. We've got one measure of it which is unfavourable, it's taking heat in. However, another measure of it, the entropy, is favourable because it's increasing. So the question now is, well, what is it going to be overall? Is it going to be feasible or not feasible when you take those two things into account? Those two factors, the enthalpy and entropy, are actually linked by the temperature. Because if you think about it, the process is feasible at room temperature. In other words, if you take an ice cube out and put it onto a table in your kitchen at room temperature, it will very quickly melt. However, if you put the ice cube and keep it in a freezer, you'd be very surprised if an ice cube did melt in a freezer if it's minus 20 degrees C. It's a temperature dependent process. It's feasible at higher temperatures, but not feasible at lower temperatures. So all that together means that yes, enthalpy is important, yes, entropy is important, but in some cases it seems that temperature might be important as well for working out feasibility. Again, don't worry too much about the understanding there. All we're kind of introducing is the fact that temperature is important as well. Putting those three things together, enthalpy, entropy and temperature, with a wee bit of behind the scenes or science, you end up with this equation called the free energy equation, which gives you one number you can calculate that's immediately going to tell you if something's feasible or not. So it's a very useful equation to use. This is it here. Delta G equals delta H minus T delta S. So we'll talk about each term side by side. Delta G is what we call the free energy. Free energy is the overall measure of whether a reaction is feasible or not. As we'll see, I'll touch on it now, for reactions to be feasible, your value for delta G must be negative. So if you type in all your numbers from the right hand side, if your answer comes out less than 0, it's a feasible reaction. If it comes out more than 0, it's going to be a positive reaction. You might think the choice of G is a funny kind of symbol for free energy. It's actually, its full name is Gibbs free energy. It was named after a scientist called Gibbs, but we just call it the free energy now. How you calculate the free energy is you take the enthalpy change, that's just straightforward what we looked at before. We take the entropy change and multiply it by the temperature and subtract that total value from the enthalpy change. So it's delta H minus T times delta S. Might look a bit of a strange equation, but it's actually not that hard to use. It is just typing numbers into the calculator. There is one thing you'd be really careful about though when you are using this equation, and it's units. Because we'll go from left to right again. Delta G is an energy value. It's measured in kilojoules per mole. So I have to make the values on the right hand side correspond to that kilojoules per mole. So down the bottom here, it's probably a good idea you take this down. Let's look at the usual units for all these terms. So delta G, delta H, T, and delta S. I've just said that delta G is always measured in kilojoules per mole because that's your standard energy units. That's going to be the same for delta H. Most delta H values are given in kilojoules per mole as well. Temperature in this equation has to be in Kelvin. Now that's fine, but sometimes in questions they might express values to you in degrees C. So you might have to convert. It's not a very complicated conversion. You just need to add 273 to get from degrees C into degrees Kelvin. So in other words, room temperature at 25 degrees C is 298 Kelvin. Final bit is delta S, and it's probably the bit where you're going to come into most problem. We've looked at it before. Delta S is in joules per Kelvin per mole. The joules bit is a bit we need to be careful about. The other two terms in this equation are in kilojoules, but we've got this in joules. In other words, we're normally going to have to divide this by 1,000 to get it into kilojoules per Kelvin per mole. So that's like a standard part of the calculation. So I have to divide by 1,000 to get into kilojoules per Kelvin per mole. So you need to be a wee bit careful with the units for these calculations. So let's have a go at a couple of simple ones here. The next page. So decomposition of calcium carbonate and gives you an equation, gives you a delta H value, gives you a delta S value, and all the questions you might have to calculate that yourself, for example. And then wants you to calculate the standard free energy change for that reaction at 25 degrees C. So I'll write down my free energy equation first. Delta G equals delta H minus T delta S. Delta G is what I'm trying to calculate. Delta H is just plus 178, don't need to do anything there. My temperature is 25 degrees C, so I need to convert it into Kelvin. I said degrees C to Kelvin involves adding 273, which is 298 Kelvin. So I'm going to do minus 298 times by delta S. Now delta S is given as plus 161. Important to check, it's only in joules per Kelvin per mole. Therefore I need to convert delta S divide by 1,000. Well, actually just do it in the equation. So I'm going to times it, or divide it by 1,000. So 161 over 1,000. Plug that onto my calculator, just being careful with how I input it. And the Gibbs free energy, the free energy value is plus 130 kilojoules per mole. The implication of that being positive is that this is not a feasible reaction. And if you think about it, that does kind of make sense. We're describing a thermal decomposition reaction in which you've done yourself, probably down in school. Though the question had this reaction taking place at room temperature, you're not going to thermally decompose calcium carbonate at room temperature. You need to put it in a Bunsen burner flame. So that kind of backs up our common sense understanding of this reaction as well. It needs to be really hot for that to work. Second reaction here, formation of calcium chloride, Ca plus Cl2 equals to CaCl2. Gives you a delta H value. It says delta H formation, but if you think about it, this equation does just describe formation, so it is just a delta H value. Also gives you delta S, and it's explain whether this reaction is feasible at 298. So plug in our values. Delta G equals delta H minus T delta S. Delta H is minus 975. Minus the temperature, it's already in Kelvin, so we're fine, so minus 298 times, again, entropy, it's given as joules per Kelvin per mole, so you need to divide by 1,000. Sticking in the calculator, being careful with my signs, should come out as being minus 750 kilojoules per mole. The question asks, is that feasible at that temperature? It's a negative sign in front of that number, therefore it is feasible at that temperature, and it will take place quite readily.